Swayam Prabha. Digital India. Educated India.
All right, so day 4 hands-on session. So um, we will start with the align model just to predict properties. Then we will try to develop a force field. It seems like some of you are actually interested in this kind of force field training. And then once we have trained this model, actually, then we can use this for general materials optimization or phonons and stuff like this. We'll show that. And there was some interest in melt quench simulation, amorphous materials. So we'll show that. Atom vision, computer vision, ChemNLP, Atom GPT, forward and inverse model. Even if you did not complete over time, then at least you can go on your own. There's notebooks and everything should be available. So let's start with AI 11, 12. So AI 11 is this guy over here. It might require, okay, it is signed in already. So it shows how to predict exfoliation energy. So yesterday we were talking about different chemical bonding, or the day before, different type of chemical bonding. One of the chemical bonding is van der Waals bonding, especially found in 2D materials. So if you have van der Waals bonding, then if you want to take one layer out, the energy that is cost for that process is called exfoliation energy. And using DFT, density functional theory, we had developed a database for exfoliation energy, and now we will try to predict using machine learning. So you'll see now on, we will be using something called Conda Collab. We have learned already that how non-reproducible things are, especially in software field as well. So Conda and in Conda Collab especially tries to have some sort of basic reproducibility guideline. So you click on Conda Collab and wait for a second. So it will change the default Python section in Conda, in the Google Colab. Note that you cannot make new environments in Conda Collab. You can only work with the base environment. So unlike other Conda. Just check everything looks okay. Any problem getting up to this point? Anyone? Yes. So this is AI 11. So if you go to the Jarvis Tools notebooks, there is artificial and intelligent machine learning and the 11th of that. Okay, so now comes the time consuming part. So this process will take around, I think, 6 minutes just to install this. Let's see. So you see the time is about 6 minutes. It took 6 minutes in the last installation. So what I'm going to do is I will just let it run here, and while it's doing this, I'll go through the notebooks, and when it's complete we can try to complete from there. So what will happen is we'll use Conda to install the packages which are Align, PyTorch, Torch Vision, Torch Audio, PyTorch CUDA, and from the channels of PyTorch, NVIDIA, I'm asking it to yes. Sometimes ask the question, should I want to install it, not install it, just call it -y. Minus quiet, because I don't want to print a lot of things. Even if I say quiet, look how many things it prints, right? So still we can have some sort of printing statements, how the process is going. It will take about 6 minutes. Once it is installed, we will need some data to train. So in this example, we are getting the data from the Align repository test set. So while it's installing, let me show you how does it look like. So we'll git clone this. Git clone is a way to download this data set, and we will work with the example data set. It has several sample data for regression for one property, sample data for force field training, sample data for multi-property prediction, and so on. Let's start with the sample data part. In this, you will see that we have bunch of postcard files, a config file, and the ID prop file. These three things you need. First is idprop.csv file. This file has the following entries: the name of the file and its property. This I think for band gap. Okay, these are 50 materials data, and for each of these you can see the. Oh, of course. Sorry, this is my always the problem. So sample data, and there's a script also that was used to generate this input file. So we took the Jarvis DFT data set, we took the auth BAT at band gap, we took 50 sample, and we wrote in an idprop.csv file, and we also stored the WASP file here. So you can generate your own data set in your way, doesn't matter. Just it should be in a format like this. Like this, yeah. And if you have never seen postcard file, it looks something like this, where we have system, any name, the scaling factor, it can be 1 usually, 3 lattice parameters, the atoms, 1 vanadium, and this is coordinates, and 2 selenium atom, and these are the coordinates, fractional coordinates. You can also work with CIF file, XYZ file, PDB file, but here we are only using postcard file. So that's the part of the idprop.csv file. Any question on idprop.csv file? None. So I'll move on. So second file to care about is the config.json file. This has all the hyperparameters. Remember we talked about the hyperparameters of the model? It will look a little ugly, so heads up. So we have certain things such as which version of Align we are using. These are git hash ID. You can keep this to be atomic number or CGCNN type features. You don't have to change all these things. You can just keep it there. There are different type of graph, k nearest number graph, radius graph. What kind of precision you want, float 32, float 64, whether you have classification or regression. So if there is no classification, make it null. Random seed is 1, 2, 3, you can put any number. Now there are two ways to specify validation, training, and testing. You can get the actual numbers, like this is the number of validation, this is the number of tests, this is the number of train, or you can give the ratio. I want 80%, 10%, 10%. If it's null, then it will read the ratio part first. And how many epochs? So epoch is how many iterations you want to do. So usually it's like 300 for a typical model. Batch size is how many samples you want to put in each of the run. So usually it's like 32 or 16. Here, because we are using the Colab, we'll try to use the batch size of 2. Learning rate is usually 0.001. We will use mean squared error as the criteria for loss function. Adam W optimizer. One cycler is a kind of scheduler. It's basically how often or how to change the learning rate. It can also change the learning rate automatically. Whether to save the data loader, whether to store or show the process, standard scalar and PCA, we can just keep it false for now. Num worker is number of CPU cores you want to use, the cutoff of the graph, maximum number of neighbors of the graph. There's a thing called LMDB, Lighting Memory Map Database. Okay, so when we make the graph, sometimes these are very memory consuming. So I think it's from IBM. They generated a strategy to store a large amount of data in a and to access time is pretty fast. So this what we use by default. It's always true. Now these were all training kind of parameter, hyperparameters. You know how many epochs. Now there are model-based parameters, like how many layers of align. So in a graph neural network, you can specify how many times you want to update the layers. So there can be align layer, the bond angle layer, the how many number of bond distance layers. Atom input features is like if it's atomic number only, it's only one features. If it's 92, like boiling point, melting point, all of those, it can be a 92. Edge input features when you have the embedding. So we have the convert the bond distance into similar feature. So you have the feature up to 80. And triplet is angles. Hidden feature is basically out of doing all of that, bond, angle, atomic feature, you have to convert your 256 feature for each channel. Whether you want to do gradient for force field or not, because it's a property prediction model, we don't need gradient, so we made it false. And you can have the weight. Remember we talked about the loss function and stuff. So here we want graph-wise weight to be 1 and others to be 0. Now because we put gradient false, it will consider it to be 0 automatically, the gradient's weight to be 0 anyway. Whether you want to do classification and some other hyperparameters, which is not maybe too much necessary. So we have now installed this package. It took 6 minutes and 36 seconds. And we will git clone this. So git clone is a way to download the repository or the code from the GitHub. So it's right now getting all the, just because we need those files as an example files. We can generate our own too if you like. So now the align comes with an executable called train align. And so that's why one good thing is you don't need to code all the things for training. You just have to give the directory where you have stored the data, where you have the ID prop CSV, config file, and all the postcard file. And the config path, the file I showed you, and where you want to store the output. So once you give this and you see this exclamation mark, in Jupyter or Colab notebook, this means it's an executable. Okay, so this is for regression task. We will run this. So now the program will automatically convert the atomic structure into graph, split the data in trained validation test. So it's saying that, let me go to the output. It's saying that there are 50 samples and I'm using LMDB data set. The maximum value was 6 EV or whatever the number was, the minimum was 0. The mean absolute baseline error was 2.38. And I am calculating line graph and 45.5. You can use multiple GPU for training. So there's a rank. Here we are using 0 only. What version it is using, and so on. It printed the hyperparameters. I forgot the name of this thing. To convert any text into this, it's called Figlet, I think. Yeah. Anyways, so the model has 4 million parameters right now. If you change the number of align layers or embedding or hidden features, the number of parameters will change. Now you can see in this one, we have training loss and validation loss. So for 0th epoch, we have the loss coming from, the loss may come from graph-wise output, atom-wise output, gradient-wise output, and additional and so on, and how much time it takes. So because we have only graph-wise output, we will see these two numbers are identical. But later we'll see when you train force field, they will be like branched out. Those will be split. So we did this training for 3, and you can see what are the folders it created. On your left hand side, if you click, refresh it, hopefully it will show. Let's see. Oh, I don't know why it doesn't show. Anyway, it should show here all the folders. So, huh? It's showing, right? Okay, I don't know why it's magic. Is it this? So it shows all the outputs. It will show how all the output created. So this one is example of regression. And if you want to do classification, you can put the same data of band gap and have a threshold. So suppose 0.01 EV, below this is metal and above this is non-metal. We want to classify this. So we'll put the classification threshold, same data set, everything same. And don't forget to remove this something called data file. So it stores all the graphs into this format. So you want to have delete it so that it doesn't read directly from there. So we'll do classification. So here it converted into graph. So here the loss function is something called negative log likelihood. Negative log likelihood loss function, NLL loss. Okay, so it calculates this and gives me the receiver operating characteristics area under curve. Actually, it's pretty worse because we have only 5 samples. But if you want better model, you can get up to 95% accurate model to classify metal versus non-metal. All right, so this was an example of single output data. You can also have multi-output data. So here is an example of multi-output. I'll show you. So in this we have the postcard file and bunch of properties. I don't know how many, a lot of them. And this was generated using a script which is available here. So this is for electron density of states. We are trying to predict up electron density of states, and they are from -5 eV to +5 eV. So here the same idea, you don't have to specify how many inputs or output it is. It will automatically figure out based on the CSV file what's with the output length and everything. Here you will notice the number of parameters of the model is 4,103,000, while that for the other model was 4,026,000. Why? Because it's trying to predict other output layers as well. So that's how your model parameters changes. Now we will do a force field training. So the force field training data set is a little bit more involved, honestly. So it looks like the following. Oh, not this, sorry. So yeah, this is gonna look ugly, okay? So get ready. Or maybe we cannot download it. Oh yeah, look how ugly this is. So in this we have the ID of that material. So here call it 1. Atomic structure dictionary, which has lattice matrix, coordinates, the element types somewhere. Yeah, here's the element types. Then you have forces for each atoms, right? And then you have stress somewhere. This is from DFT data. So you have done a lot of DFT calculation and store the data in this format. And the stresses, which is like I think it's 1/6 representation. So that is one entry, one material ID. And then you have I think for 300 or 500 materials like this for copper only. And then we have this is called mlearn data set for copper, for germanium, lithium, molybdenum, nickel, silicon, and so on. This is one of the first thing people try anytime they develop a force field, just to see how they perform on this data set. And you have done the MD and you have stored all the energy forces and stuff. Yeah, structure energy forces, yeah. So in this example, I would like to show you there are certain changes in the config parameter. So sample data FF config. So here we will have, other than the default parameters, you will have calculate gradient true. Let me see if it's there. Yeah, calculate gradient true will ask basically to calculate the forces. And then here, because we have stress as well, you can have stress weight at gradient wise weight, graph wise weight, and so on. And you can tune this. And based on the tuning, you get different accuracy of the model. No, this is from scratch. We are not tuned anything. It's learning. Yeah, during this, the weights are fixed, but these values are fixed. So what I would do is, suppose I start from scratch a model, I'll see how much loss it is. I'll show you. Then to balance it, I'll try to balance it in a way so that all of them get equal amount of attention or equal amount of weight. Yeah. So let me show you. Here is an example. So this is for a really small force field data set. Yeah, one part. This particular example is not, but that copper example was. I'm running some other small data set, not for all copper. So here we have, let me see, this is example sample data FF, and the ID prof for this is this. I should have shown you this. So here we have like uranium, nickel, germanium, all those kind of things for like 20 materials from Jarvis DFT. So here we saw we are taking smaller number of parameters just for fun, and it also shows you what kind of GPU you are using, what's the maximum memory, and so on. So here you will see, in addition to having graph-wise loss, there's a gradient wide loss, there's a stress wise loss, and those things add up to give total loss. But here you can see the gradient loss is much smaller compared to graph. So there is lot of attention will be given in energy rather than gradient. But if you want to get more accurate gradients or forces, you have to multiply this by something like, I don't know, so 100,000, something like this, to make the number almost equal to the graph level. Actually, no, that's not right. You see here it gets smaller. There's something after like this. So you need to multiply by 1,000 or multiply this by 0.001. Then the weight contribution becomes on the same level. Same with the stresses and so on. So does it make sense? Everything clear? Any questions so far?
So is there a parameter to do that multiplication, that configuration?
Multiplication?
Like to make it equal, like the graph?
Yeah, so you did the first training, you saw this is like it needs to be fixed. So you will go there, modify the config file, whatever it was, instead of 0.01, put it like 100 or something, and then run again. Yeah, it's like a hyperparameter thing. Okay, so here, so here will be, because we want to compare different type of model, we'll use Jarvis leaderboard to get a exfoliation energy data set. So we install Jarvis leaderboard just to check everything is fine. And to get a data set, there is a command called Jarvis populate data. Okay, so if you give a name of a benchmark file, again, you don't have to follow this process. You can have your own data set in format. This is just an example. I want exfoliation energy data set, so it will populate all the POSCAR file, ID prop file from internet. Download this, populate in a format that this model can take. So right now it's downloading this 40 megabyte file from internet, unzipping it, and it will look like this. We have these are all the POSCAR files. Okay, it looks like JVAS, but these are all POSCAR files. And you see there should be config file and the ID prop file should be there. There is ID prop file is here, so it will right there. So we got the data that we want to train on, and it also writes what should be your training, what should be your validation, and all these kind of things. So in this, we want to have 650 as training, 81 as validation, and 81 as testing. Okay. So we will have a new variable called ntrain, nval, ntest. We will download a sample config file from internet. Remember wget to command to get the internet data. Load this as a JSON file. This is the default one looks like, and we'll update that parameter for ntrain. So you see this is how we update the parameter. Config ntrain equals to ntrain, the variable we defined earlier. Batch size, usually you need 200 to 300 epochs, but here just be working with 20. And the batch size can be, depends what kind of GPU you are using. So if you are using something like A100 or something, you can put like 500 batch size. If you are using like T4, you can put like 20, 10, something like this. Yeah. Now we will store this or dump this JSON file called temp config.json, and similar to the earlier, we'll ask train align to train the model for this, where we'll give the root directory, config file, and the output directory. I think it takes like 5-10 minutes, so we don't have to wait. But I want to show you the process that it has a maximum value of 948, minimum value, mean absolute deviation, baseline, and so on. So it's converting into graph right now. So we'll do its training. I think it's pretty fast, which is good. So once this training is done, I also, whenever I publish a paper, I do this Conda environment export, and I store this as a supplementary file, because this should reasonably give you a reproducible environment, because everything is like all the version, everything is fixed. Okay, so in the output file, it stores the test data results, and this is just one way to access this. We'll get the target out, so you know the actual test data set, and the prediction out, which is the predicted data. and it looks like this, a straight line thing, right? So even with the just 20 epochs, we can get a mean absolute error of 41. Now, if you want to see what are the other models, search for exfoliation energy. So the best model is 40.88 milli electron volt per atom. So ours was reasonable in terms of 41. Okay. So this is how we, and then once the model is developed, you can store this in a CSV file. I will not do that here, but you can automatically upload your data to Jarvis Leaderboard if you have a GitHub account. So let me see if I have it here. Yeah, you have to give your username, what is your email ID, GitHub token, then it will automatically clone the Jarvis Leaderboard, add all the necessary file like metadata file, config file, run script, then add the files, make a pull request to Jarvis Leaderboard and send an email to our team. All of that automatically. But you need this, your GitHub token. And then just pip freeze another way to see what are the things which is installed. Let's see if it's finished. Yeah, this did finish in, it took only 2 minutes, which is not too bad. So the conda environment export, usually we write like this, environment.yaml, and we store that YAML in some repository. Oops. Oh, I didn't forgot to maybe. Here's the plot again. Oh, this one here. Okay, so you can also see the data. So it has the ID, the target data, and the prediction data. Now you want to train a machine learning force field, similar idea but for silicon. I want to show some of the things we want to test other than those scatter plot, as which are important for material science application. And this will be hands-on number AI12, which is right here. Okay, so unfortunately we have to do the same process, takes 5-6 minutes. That's something we cannot skip. So if you had your own cluster or laptop, then you don't have to install this over and over. I don't know what's going on, but yeah, you can install similarly the align in the previous notebook. Here maybe it's like a different way, but it does the same job. So here we will download this silicon data sets. Similarly, we showed you for copper, the ID, atomic structure, and energy and forces. We get it from internet, and we have some default parameter set. And for that particular benchmark, the number of training and validation and testing are well defined. 214 for training, 25 for validation, and 25 for testing for 30 epochs. So we will update our config file, and then very same process, this train align. Then it will remember for each model where it gets lowest loss, it will save the model automatically wherever the best loss is achieved. And then let's just try to go here. Okay, so let's do the installation part. So once you install and run this example, it will give you this thing called bestmodel.pt, which is the weights and bias floating numbers in PyTorch format. That's how the model looks like. It's a bunch of numbers, megabytes of numbers. So that's why machine learning models are not like an equation or something. They are just numbers. And these models you can share with the world if you like. So, and you can load it like this. This is one way to load the model, and there's all yeah.
While loading, how does it identify what kind of architecture it has?
Yeah, so maybe I can show you. It remembers all of that information in the .pt file. Yeah, they have some format for this, well-defined format for this. So you know this number will go to align layer. This will go to GCN layer. All of that. I think it's still running.
Kind of store the whole class kind of.
It stored the exactly. So you are right. So because it's a class, it can just dump that class
In binary format.
in a binary form. Yeah, binary format. Oh no, I want to show you something else here. Let's see. Okay, so there's something else called calculator. While it's doing this, let me introduce this idea of calculator. There is in atomic simulation environment, there's also a tool for running a lot of calculation. If you search for ASC calculator, so you'll see they have made some provision that you can run multiple methods such as align, abacus, big DFT, ChargeNet, FLIR, GPaw. We run GPaw previously. Orb models. There are many methods you can run models, right? So these are called calculator because I have the atomic structure. I just attach a calculator and get number like energy forces. It's like all modular in that way. So that's the idea of calculator, and we can convert that model, the PyTorch file, into a calculator like this. And we can, once you have the calculator, you can attach atoms.calc equals to that calculator. And then from there, you can get potential energy, forces, and stresses for any arbitrary crystal structure. So don't worry about this, but here what we're trying to do is predict the test data set error in forces, energies. So this is the energy error, total energy error. This is the force error. Okay, this all looks x equals to y line. Stress was pretty bad because we did not train on stress. And so these what a machine learning scientist would do up to this point: put a scatter plot, MAE, RMSE, R square. But as a material scientist, we have to be more careful. One thing I always do is equation of state. So take the silicon. This was, I think, for silicon. You isotropically expand and isotropically contract, and see whether you get a local minima somewhere or not, and looks smoother or not. So here we are getting some. I mean, our grid was coarse, but we get this kind of well-known curve for equation of state. You can also relax structure. So put any postcard file for silicon because it was made for silicon. Just paste it here, and then it will convert to atoms. And you give this atomic structure to this general relaxer function, which will basically try to optimize the atomic position, lattice parameter in a way the energy and forces are minimized. And then you can get the relaxed atomic structure of silicon. So I think here in this case, I had arbitrarily given the lattice constant 5 angstrom because I did not know what's the lattice constant of diamond silicon. And at the end, it gave me a lattice constant of 5.59 or 5.60, which is closer to experiment. Another thing I'd like to test is this, where I have, let me try to remember this one. Oh, check translationally equivariant. So you basically take an 2-atom cell, silicon and this silicon, and you kind of, the position you're trying to move it like this. So you have a silicon atom cell, the first atom is fixed, the second atom is translationally variant, coming back like this, okay? And see how the energy changes. So when the atoms are on top of each other, energy will be very high, and where they're like on equilibrium position, it will be low. You can do in along 001 direction or 111 direction, right? And see how the energy changes. You can run MD with this. So this is how we run MD with this kind of calculators. So you have an atomic structure. So here we are getting from Jarvis, but you can have your own postcard file. And then you have to see the time steps. So here we are using 1 femtoseconds. We're going to run on temperature 3500 Kelvin for 1000 time step. And then we're going to run on 300 Kelvin for 2000 time step. So melting and quenching. And there are some parameters. We start with an initial temperature of 3500 Kelvin and do NVT. Remember we talked about NVT ensemble? So we do NVT Berndsen thermostat, and just this is how we run MD calculation. So it's running, for each time step, what's the temperature? Temperature should be almost constant up to this point, and then start decreasing. And luckily, it also produces something called traj file or trajectory file. You can take this trajectory using ASC trajectory reader, and you can make this really fancy animation, I believe. So first, this is a radial distribution function. You can see the first peak is so sharp. That is a characteristic of any amorphous material. And this is the animation. So it's for each snapshot, it had calculated the energy, the corresponding RDF, and the atomic structure. And you can see how it's changing the RDF and so on. Don't worry about this. Don't worry about this. Is that it? Yeah, I think that's it. So we do not actually run the thing because it takes like 3 minutes to install the software itself. And we have to do it for each notebook, which is annoying. But you get the point I'm trying to say. Yeah. Any questions on this part?
So we are going for silicon and training the model. Can you predict other material?
Yeah, so we have, suppose you want to looking for database, right? So we can go to you can have your own data set. So there is a script where you can take a bunch of WASP output and convert into this format for your own data, and it will do the training. And we have also given the 300,000 data set, I think somewhere here. Is it this one? No, this one. Fixture-based data sets. So here we have something called Align FF data set. These are 300,000 materials with energy, forces, and stresses for different materials. So instead of doing this for silicon, we can just download this and give it exactly the same format. It will train the model for you. It will take a few days though. It will take a few days. You cannot do in Colab. One of the specialty about this particular model, there might be better accurate model, but we try to train the model is very cumbersome to set up process and everything. But our goal was at least to make it easier for people to use, just a command line kind of thing. You don't have to know too much coding and this and that. Oh, no. Okay. Yeah. Oh, it's in the Align GitHub. Oh, what did I type? ALIGN GitHub. Yeah, this one. So this has a code that we developed. All the scripts. So these are how our models look like. I don't want to scare you, but this is just the model part where we have like hyperparameter as base config. How we deal with the edges of the graph. So the main part is this align model class, which has atom embedding, edge embedding, angle embedding, align layer, GCN layers, and this is how the training takes place. But again, you don't have to know this part, but all the code, everything is available online.
So if you want to develop a new graph model from scratch,
Mhm.
You are using DGL, right?
I am using DGL. Yeah.
So is DGL adaptable to any kind of configuration?
Yeah. Many people use that for their own, and you don't have to use DGL. There are other things too, like PyTorch geometric and stuff. And some people write their graph library in PyTorch itself, so that can also be done.
For that, you have to develop your own functionality.
The main part is batching. So when you have different materials, one material is 10 atoms, one material is 1,000 atoms, and you have a batch of 500 or 200, how do you put them together is the question, right? So what these softwares do is to try to preserve all the nodes and edges where it can still be in one way, in one batch, but still preserving the information from where it came from, so that it doesn't, when it predicts energy of silicon, it doesn't mess up with aluminum oxide. that's the beauty of batching from this software. That's why we used it. Else you can use whatever PyTorch only. And it's very fast to do a lot of operations because the under the hood is all C++ they have written. They are not, it's not Python based code. Yeah. All right. So this was, how are we doing with this time? I think we have to do 30 more minutes. You have to suffer for 30 more minutes. Can you believe this?
Sir, is there any model deployment kind of thing to if I get
Yeah. This sure.
it will give some amount of
Yeah. Oh, a morphostructure, no, but we have a model that can do right now for equilibration of structure. So if you go to the, just optimize the structure. So the Jarvis has, okay, I forget how to move this back. Anyway, if I go to this web apps, there is something called align force field. Yeah, click on this. So here,
So when it's optimizing the structure, is it just calculating the force, just energy or the force also?
mainly forces on atoms. You can do both energy-based minimization and forces. We do
So
force
if you
based.
based on energy, then you have to generate random structures and see whether
Yeah.
it's low.
But it's like trying to minimize both, right? You basically modify the atom slightly, move the next step, and so on. Vary the lattice parameters. So web apps, align force field, and it takes few seconds. Okay, so these is my crystal structure as input. I'll give and submit. So it will do the optimization and give me the optimized structure. Hopefully, takes few seconds. You just want, okay, so you have to run on the Colab. Just put the postcard there. Yeah, there's a example called run melt quench. I think we're gonna talk about that. This is the fourth one. Two more. We'll get there. So yeah, it did the equilibration. This is the input structure, and this is the output structure. It's optimized output structure, and we are going to make it an API too. So you don't have to go to the website. Once you have an account, a user and a password, then you just, do you know curl? Curl is also a command to post things on internet. CURL, just like wget. So you do curl Jarvis whatever .align post, and it will submit the file, do the calculation, and print you the optimized file. So it will, yes, it will be cool. Yeah, it's actually already there, but I have not advertised too much because then people will be putting everything there. So we are working right now is how to cap the number of computation. Like one person doesn't take the entire compute power. That's the part we still have to work on. Okay, so what did we work on? We had the force field. I want to quickly show you this 37 notebook, which is how to optimize different structure and get phonon density of states and how to generate interfaces. So again, we have to do the same painful thing of Conda Colab, but we assume that it works, okay, at this point. So here we are working on at least 20 or 30 materials like silicon, aluminum, germanium, I don't know, aluminum gallium nitride. These are the corresponding IDs. This is a function we wrote to relax any atomic structure. So you give an atomic structure any calculator, force max tolerance, and the steps you want to do, it will automatically relax that atomic structure. So we will loop over those Jarvis IDs and then give that atomic structure to this function, and we will also predict the EV curve, energy volume curve, and we will also have the phonon band structure for that material. So you see, this is it download the atomic structure of silicon, run the relaxation because it was already kind of relaxed. So it was very fast. It gave you the relaxed structure. It did the phonon band structure. Remember, there was no phonon training in our data set, just bulk materials. This is the equation of state, and this for all aluminum, copper, titanium. So you see there are some negative modes as well. So it's not always perfect, and so on. So you can put any kind of arbitrary structure. Let's see how the installation going. So this was for bulk relaxation, but sometimes we want to deal with interfaces. So here's an example how we create interface. And for this we use a code called intermat, which we already talked about a little bit. We install this and we give a postcard 1 and postcard 2, which are film and substrate. Okay. So we make an atomic structure from this, and then in this, again, this little bit details, but we have a class called interface combination, where you give the film index like 100 milli index for the film and 100 milli index for the substrate. And I do not know what should be the equilibrium distance. Sometimes we do not know what should be the equilibrium distance between the two surfaces. So we give a range from 0.5 angstrom to 4.5 angstrom with the interval of 0.1, and let a line calculate the energy for all of them. And we can plot it, and it looks like this. So the energy where it's optimized is this. This is where the optimum bond distance would be. Now, even we have got this optimum distance, if you put it together, sometimes atoms are still on top of each other. The energy will be pretty high. So what we want to do is move in x and y plane to get the equilibrium position of the material. So we take the same postcard 1, postcard 2, and here we use the separation that we got from the previous step, and then we will vary the xy plane displacement, which is at 0.1 angstrom fraction coordinate. It will try to move in x and y. Okay, and we get the energy from a line. It will look like this. So at where they are red, I believe there's like high energy atom on top of each other, and blue is where it should be in good position, where it should be low energy. And once you have made this structure, now you can put in DFT or something to calculate like band alignment or whatever you're looking for.
How does it take care of mismatch? That is,
So we have this code called Zur, right? Zur algorithm.
sometimes it kind of generates a lot of like very big
Yeah.
structures, right?
Yeah, sometimes it is. So, but I think the Zur one, especially for this kind of materials, it does pretty nice job. Sometimes you have to vary the maximum tolerance you want to have more than 8%. Sometimes you have to have maximum area to be more than 500 angstrom square or something. Sometimes it gets stuck, but for many cases it does get the good primitive cell from each of the surface and film to put it together. And the thing is, once you generate the interface, you can put that postcard in the film. Then it will be like the combined surface on top of another interface. So you can have multi-layer, and the same process will be there. Okay, seems like this is still running, the installation part. So I'm not going to run this examples, but feel free to. My favorite part is the interface of this notebook. I like to put a lot of interfaces, and you can make grain boundaries and stuff too with this kind of code. So what is grain boundary is basically you make interface and slightly rotate it. That's all it is. So you can. I have never tested it, but I think somebody might investigate the different type of grain boundaries and how does it energies look like and stuff like this using this kind of code. This is the area which is not tested yet. So food for research thoughts.
Have you validate it like you by comparing it with the experiment or maybe stories?
For the lattice parameter and stuff, for the interface?
Energy, maybe.
Energy, yeah. We have done some like this kind of curve you said, right? So this one, we have tested for some systems.
So this is the error.
This is just the energies with respect to the distance, and we had done the same system with DFT and compare how does it look like. It was pretty reasonable. For some system, of course, I'm not saying for everything. My favorite part is this part where it can actually be very useful when you want to calculate the low energy structure. Because what in past people did, they just do the Zur algorithm, put the small unit cell together, and this is my structure. Nobody want to do the XY scan, but it's quite important. And actually using this method, you can also calculate stacking fault. Do you know stacking? How many of you know stacking fault? 10%, 20%. Stacking fault is very important, especially you have like alloy system or metal system like this. So you want to calculate where is unstable stacking fault, stable stacking fault, and based on that your dislocations and other things are guided. So this can also be useful for this kind of application. Because this what we calculated, if it's for similar material like aluminum and aluminum, it will give you a generalized stacking fault plot, and you'll get like one small minimum and one large minimum. The small one is called stable stacking fault, the large one is unstable stacking fault, and these are something you're going to compare with experiments also. So this was this notebook. I'm going to disconnect it. How many of you work on interfaces? One. Wow. Interfaces are very interesting.
Some projects will-
Yeah, yes, very interesting subject. Yes. That's a good point. The same, so liquid or amorphous or molecule, you can represent as a POSCAR file. Use the same code there and see how it works. I have not tested it, honestly. One of my postdoc is working on like amorphous and crystalline material interface. She says it's very tricky. So it can be like when you're finding the lattice mismatch and stuff, smaller cell, it can be tricky sometimes with the amorphous structure, but it still works for many cases. But same format will work, yeah, for liquid and solid. So again, we will install the software as usual. I'm not going to do this. You guys get the point. Install the align package, and then some importing the libraries. And we specify Jarvis ID here, but you can have your own POSCAR too. You just have to make this atoms object somehow. So atoms from string, or there's a function called atoms from POSCAR, atoms from string. Then from string it will generate the atomic structure. And once you have this, you will get the dot set calculator equals to calc, and the calc is here the align calculator. And then again we'll do this 5,500 at 5,500 Kelvin for 1,000 steps, and 300 Kelvin for 2,000 step with 1 femtosecond time step. And I think this is for silicon. I think we saw this before. So this is the radial distribution function, how does it look like, and this is the movie we saw before. And another is the example of aluminum oxide. Here the Jarvis ID is 32, but again same drill. We ran it for 5,000 Kelvin and 300 Kelvin, and because it's aluminum oxide, atoms doesn't move much. You'll see. Too many atoms. So still it's like this. There are some peak, and you see how the aluminum oxide amorphous structure look like. There is a silicon oxide amorphous structure. The silicon oxide. So earlier force field, they could not keep the temperature almost constant. It was like crazy varying. When your force error is very high, you won't be able to conserve the temperature, and that's one way to test whether your force field has some reasonable forces or not. Okay, so just do NB with this. Do a melt quench of silicon. You will know whether it's a good force field or not. Silicon oxide, aluminum oxide. You just run this same script or similar script, you'll have some idea about the quality. And of course, you can do vacancy formation energy, lattice constant, and stuff like this, which is a part of CHIPS FF.
How do you pass temperature to the model?
How do you what?
Pass temperature to the model. Like, where does it
Oh, pass temperature to the model. So we have the calculator, right? So here we have this DIN called NVT Berenstain, and we have the atomic structure that we created, the time step, the temperature starting point, and we are writing in the md.trach file, and we attach this printing function, like how often it should print and everything, and it's done for so many steps. That's it.
So is it not
And set temperature.
input parameter to the model? It is just some
Yeah, model is fixed. Model is not being. Model will give you the role of model is given atomic structure, give me energy force. That's it. Now these calculator or the runner are doing all the job.
based on a particular temperature, it will just
Yeah.
a lot of configuration.
Yes. Not a lot of comparison, but it will just move based on the energy and forces, and based on the NVT principle.
So the NPT principle temperature will come.
Yeah. Yeah, so they will be printed here, I think, as well, and it's also stored in this .traj file. So I think this is the input structure, first one, and at the end, after all of that, it writes the output structure, and this and this is the RDF, and it's also stored in a file called mdtraj, and there's a function to convert mdtraj into GIF file animation. So this is what we are doing. So we took the mdtraj file. Let me see. Yeah, we read this in this format and convert into a GIF file. Where is the GIF file? Yeah, this is the part how you make the movie. Animation.save GIF file. So how much time we have? Maybe 5-10 more minutes. So I wanted to show you this Atom GPT model and maybe Atom Vision. Which one do you select first? You have two options: Atom Vision, Atom GPT, CAM-NLP. Which one? Atom GPT one. Okay. So let's try with Atom GPT forward model and inverse model. AI 31 and 33. AI 31 is forward model. So same stuff. Install Conda Colab, install Atom GPT. This one we'll try to run. Okay. Boring. I'll move forward with this. So we install, similar to the align example, we will generate exfoliation energy dataset from Jarvis leaderboard to get the idprop.file. Now we are familiar with this idprop.csv. There are 650 training, 81 validation, and 81 testing. And similar to the align, there is a config file for Atom GPT, where you can specify where the idprop file is, what model we are using. So here we are using something called Google Flan T5 model. We can use GPT-2, but those models are a little big and they might give some error on Google Colab. Google T5 model was one of the earliest but still very powerful transformer models. We'll use batch size of 5. These are some hyperparameters. I think this is when you write sentences about each crystal structure, what's the maximum length to take from that, I think, if I remember correctly. Latent dimensions. So once you write the text, you'll have the hidden, you'll tokenize it, and then you have a hidden dimension. That hidden dimension size is 1024. How many training, testing, and then what it's doing is it's taking the idprop file. You have the property and the description of that material, which is written by CAM-NLP. Like for example, sodium, zinc, phosphate, crystallized in tetragonal symmetry, this many bond length, and so on. All these are done automatically. So this is again forward model. Okay, this is not inverse model. So we convert it into text, and then you see this is the train loss, validation loss, test loss, and how much time it took. And this is the exfoliation energy plot that we did for align as well. 39 versus 41 in the previous case, so slightly better in terms of MAE. And you can save the model like this. Yes. Yeah, this is how you save the model, load the model, and suppose you have a new postcard file, you want to predict the property of this model, then you will use the atoms.describe, which is a, if you jarvis.atoms, if you put .describe, it will write you the NLP output, the how it describe chemistry of that in a sentence. So it will look like this, for example, MS2, again this is a simple example, MOS2 crystallized in hexagonal group, and then you'll have the prediction. Suppose for that new output, the new crystal structure, you will convert it into something called input IDs. So this is called tokenizer, where you take the text and convert into token, and that token is fed to the model. So model is fed with input IDs, and the whatever the outputs are still tokens. That tokens have to be again decoded, right? It has to be decoded. Here we had only one prediction, so it's just one number, like 103, whatever exfoliation energy it was. So this is the process of training the model. Of course, under the hood there are a lot of coding, of course, right? But the idea here is to make it simpler to use. I'll try to run this a little bit. Let's see. Still using GPU. So here you can see it's not using any GPU RAM right now, but when it will start actually training model, it will become like 4 GB or something. So if you want to saturate your, take the full advantage of your GPU, you increase your batch size until you get memory error. Okay, so like instead of 5, you'll put like 10, 20, and where it saturates. That's the one thing I really like about Colab. You can do this kind of analytics in real time. I'm not a sales ambassador of, by the way, Colab, just to let you know. Big disclaimer. Okay, something happened here. What happened? Did we install this? Oh, we did not install AtomGPT, of course. So since the interest of time, I think you guys can run it, and if there is an error, please let me know. I'll explain the inverse one, which is more interesting, I believe, which is, what's the number? 33. No, 32. Sorry. So same process. We install the AtomGPT with Conda and everything, and then we generate the same exfoliation energy. So here the idea is, instead of predicting from postcard to exfoliation energy, we want to have exfoliation energy to postcard. Okay, but the format of the data is exactly the same, id_prop.csv. But here you'll notice the model we'll use is this. Instead of the T5 model, we will call it KNC6 AtomGPT model. This is one of the model we'll be using. And the previous example, if you remember, had an executable called AtomGPT forward. That's how we know that I want to do structure to property. But in this example, we'll use AtomGPT inverse executable, and then it will do the inverse model. So it will, okay, let me see if it's installing so far. Okay, let it run there, and let me show you. It's once you've downloaded the data set to train on, specify the model, specify the executable, then it will do something like this. It will download the Mistral model from internet. Well, not Mistral model, but my model, AtomGPT model. You can start with Mistral 2, but if you start from there, because we have only like 5 samples, it will give you garbage outputs. It's good to have some sort of model like this. And the loss, again, we are just doing for 5, and this is the prediction on the test set. So you see it's actually predicting postcard on the test set. Target material is this, and the generator material is this. So this has 2 force stoichiometry, this has 1 2. So it can be slightly different, but you can see it's doing a decent job in terms of, like, it's not TV, it's TA still, right? It's still this kind of where it can when it generates elements which is not part of periodic table, like some TN or TP or something. This thing is called hallucination, and this is a very good, like very detailed research about identifying how does a model hallucinate, generate something which doesn't exist. Somehow this Mistral model, again, I'm not ambassador of Mistral model, seems to not to hallucinate much. And the part I wanted to show you is like, let me see if I have here. Yeah, I wanted to vary this. So just have a normal formula like FEBN or type some other formula, it will generate the crystal structure. So my goal is, our team's goal is to just have this as an app. So you can just type it, generate with this crystal structure, and here's the postcard. Yeah. And then relax with align FF, and see whether do X-ray diffraction pattern or something. Interact with Chem and LP to find any papers on this. It's like an agent kind of thing. It's going there. They're still installing. I don't know. Okay, there are some other things too. It's commented out, but suppose you want to make a database out of this. So you can make a for loop of all the periodic table elements, 100, as for loop 1, for loop 2. Property can vary from 0 to 100 or something like this with a grid 10. And then for loop it and give it as a prompt. It will generate a lot of structures. Okay? And that will be a new kind of database which may not exist. Also, I didn't mention this large language model has a lot of parameters in it in terms of statistics. One of the key parameters is called temperature. It's like basically how crazy the model will be. So the craziness can be like 0.1, 0.2, 0.5 up to 1 and so on. So you can vary that too to generate more and more crazy outputs. So there are multiple sampling procedures to make a huge database out of this model. Yeah. Yeah, I think it's taking too long, so let's disconnect this because we have 3 minutes left. Yeah, so we did Atom GPT. We did. Let me quickly look at 26, 28. I'll just skim over this, and then you guys can run it if you like. But the Atom Vision model, it will be just for classification of images. So we will, similar to the Atom GPT or Train Align, there's an executable called Train Classifier. And in this, what you give is, what is your train folder? You have a folder where you have all the images in a subfolder called like 0, 1, 2 in a subfolder, and you put all the images there as JPG file or PNG file, and the test folder and batch size and how many classes you have, and automatically it will do the training for you, and you can see it can get up to 70% accuracy. But here, it's just for sample run. And then, is there other plot? Maybe I want to show some other, like how to create images. Yeah, this one. There's a Colab example here. So if we have a postcard file for graphene, it will be this kind of image, right? And there's an app also in Jarvis. I think it's called STEM. Let me see. Web app. STEM. So this is my postcard file. This is the output I want, 256 by 256 with a power factor of 1.7 with a Miller index of 001. I hit submit, and hopefully it will give me the STEM image of this. What was what? Yeah, I give a postcard file. Now, before this, what was it doing? Oh, you mean how to get the example image. So this is part of, if you go to the Atom Vision page, there is a notebook here called Open in Colab. And then, blah, 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 all the installation part. And then here we have a executable called Atom Vision script stemconv and file path of my postcard and generate this output path. That's it. It will generate you this image for any postcard. And of course, you have to specify Miller index and all these kind of things. But the default was 001. Yes. It's computed, yeah, right on the spot using the Rutherford model. Okay, so last one is ChemNLP. So it also has some Colab example, which is also linked in the Jarvis Tools notebooks. So here I wanted to show you that word classification. So we will download the condensed matter articles. I think it's 300,000 article from internet. Same with PubChem articles. People are doing all kind of fun stuff with these data sets. So this is the histogram that we generated. So we can load this in a pandas and make a category plot. And you can see the most frequent articles and so on. Similarly with PubChem dataset COVID-19, you can make a TSNE plot. So ChemNLP has something inbuilt called TSNE. So it will give you a pandas data format. Suppose you want dealing with 1,000 papers only, then it will look like this. Same with PubChem, and you can do an executable called scikit classification, and give the CSV file, and what's the column name, what's the title, like, you know, this is my category, like condensed matter physics or so on. What are you looking for? Like the header of the text is in the title or abstract or something. Then it will, you can see this is the title and the category 0, 1 to 5, whatever it is. And it will do the classification up to 92% accurately. You can do this. Confusion matrix, we talked about it, you know. You can generate a confusion matrix and upload the file in Jarvis leaderboard if you like. Let me sign out from this. Come on. This part doesn't need to be recorded. Anyways. So any questions over the million of things we talked about? Yeah.
So I'll use my data set.
Mm-hmm.
It is already pre-trained.
Yep.
So we work for, let's say, molecular system or nanoparticle kind of system, which is, let's say, in a big platform box, there is a say, nanoparticle.
Mm-hmm.
It will work for that.
You have to test it. I don't know if it will work or not.
It is mainly for crystal structure.
Oh yeah, we have tested for molecules too. A lot of molecule structure. We have tested for. I didn't talk about it. There is something called catalysis project. I don't know if it's there somewhere. Yeah, there's this catalysis project where you will train the model on perfect materials only. There's a substrate. You put the molecule, and it will predict the adsorption strength using the pre-trained model. No training needed there.
No, that is also periodic system.
Okay.
I'm talking about the zero dimension.
Zero dimension, there's basically what you have is there's a lattice vector which is used. That's it. In terms of structure, the periodic image do not talk to each other. So if you have like a 50 by 50 by 50 box and there's a benzene molecule, it's an isolated system. Then you can put it there and see whether it works or not. I think I have tested for like some well-known molecule like benzene and all these kind of things for energy, formation energy, or cohesive energy. Seems to do reasonable job. Yeah, yeah. So
That periodic edge will not be there, right? In those cases.
yeah, because it's very far, the contribution will be very minimal.
So whatever cutoff will take, it will not come. The other
Yep.
contribute.
Yeah. So one good question is for this kind of isolated system, many other models fail because the way they are designed, they are not supposed to make a complete graph because they don't satisfy this 4 angstrom criteria. So what we do is like we keep adding multiple copies until we have certain number of graphs. So just to make numerical stability, that's it. But you can try isolated molecule and stuff too. One of the fun thing many new companies are trying is for this kind of models is for drug design. Because these models can model really thousands of atoms, what happens if you take a protein and put like aspirin molecule to it, whether it's stick or not, right? In a particular solvent. So those kind of models people are doing as well. And because these are energy-based models, these seem to be pretty well in terms of performance.
So how big
Ah, good question. So there's a scaling analysis in the chips FF. Okay, maybe not that. Okay, so this paper. This postdoc, I'm really proud of him, Daniel Wines. He does really fantastic work. So he did this scaling plot.
In terms of how much resources is it used?
Yeah, so here you see up to 10,000 atoms, at least for most of the models. Why can't I make it bigger? So up to 10,000 atoms, it goes like this. For some models, this is a meta model, Facebook model. Somehow they did some, I don't know what they did. There are a lot of parameters there. So it's almost as slow as DFT. So, and there are some models like Align and MatGL. We are very close to so one of the fastest model. So MatGL and Align FF. And then you can see you can model up to 10,000 atoms in how many seconds is it? 300, 200 seconds. So, but I have seen, that's my postdoc told me, after 60,000 atoms, all of them start to slow down. It's very, very slow. So,
So this is MD or relaxation?
this is one single step calculation.
Timing.
Energy, no, this given structure give me energy forces. This one inference point.
Kind of an SF cycle.
Huh?
Kind of an SF cycle. Just
Not even SCF. The one point in the SCF cycle. Yeah, you can call something like this, like one prediction from one structure, one inference. Yeah, it's so basically you give a structure, and for each model, how long did it take to predict the energy? That's it. For each structure. So if it's like, yeah, it should go linear. That's what the point is here. But after 60,000 step, we run into the RAM memory bottleneck. It might be still going on, but the RAM will saturate. So there is a model called ORB model. I think it's part of this. This is very interesting. This is a company, Orbital Materials. That one, that's what my postdoc told me, is the most efficient in terms of RAM memory, and in terms of speed, Align FF and MatGL. So you have to see which one do you. If you have a lot of RAM, use MatGL or Align FF. If you have a lot of memory, then use ORB. Did I say the opposite? You get the point. I mean, you have to test it out. ORB is good for less memory requirement, and the other way around, vice versa, whatever.
so as we are increasing the number of atoms, matrix size will increase, like whatever multiplication.
The graphs is like really huge.
So it is looking like a straight line once you are going from like 5,000 to 10,000.
Yeah.
Kind of straight line, right? So are you like increasing the resources that you have there while doing the calculation? Like,
No, it's
are you
fixed.
making more
Fixed.
parallel or the same resources?
Oh yeah, we could parallelize and stuff. Again, we have not played with this. This is just like dumb way of testing this kind of efficiency. But you can have like different. This is on CPU, not even GPU. On GPU, it will be much faster as well. And multi GPU will be hopefully more faster, right? I would assume. Mm-hmm. Mm-hmm. Oh, CDVAE. This one. Yeah. What did I do? So whenever I do full screen, it goes crazy. So I'm going to stay in the local screen. This one. So this part, right? How does it predict the crystal structure? Yeah, so it's basically encoding means those hidden features, making those hidden features for any new prompt. So suppose you have crystal structure database and you have property, right? And then you can take the crystal structure, make into a graph, make the embedding part, and write a model that given the embedding, predict the number of atoms, predict lattice parameters, predict the coordinates, elements. So this is my from atomic structure to encoding to this kind of thing, and decoding from this, add a lot of noise, make it complete noise, and from this denoise to complete atomic structure. This is the process. If you can learn this, then if you have a hidden feature or property, which is basically a prompt, right? It will try to decode it to make a crystal structure. Yeah, so basically, once the model is generated, we are training on 10,000, 1,000 superconductors. Now we give some random chemical formula, which was not in the test set. It will generate the crystal structure. Same like the atom GPT example I showed you, something like this.
You have to test it, right? Whether it is superconductor.
Oh, of course, yeah. You have to. So first, what we do is, at least so in the table, we have the align based TC model, so forward model, which is already pre-trained. We saw that whether it's high or not. If it's high enough, then we do DFT calculation to validate. Good. Okay. Thank you again. It was fun.